Okay, now we will talk about unstable atmospheres, because the unstable gymnast is the gymnast who is at the top of the uneven bars doing a handstand. If anybody nudges her, she will never return back to that position, that original position, without exerting a lot of energy. So while our systems in our universe tend to equilibrium, they tend to equilibrium without extra energy. Unstable equilibrium in an atmosphere is a torrent of rain that comes down. The unstable atmosphere was the storm cloud that was sitting over your city. That was an unstable atmosphere. It used that unstable atmosphere to grow in vertical height and grow and grow and grow. When it's nudged by a wind or by a little bit of frontal lifting, it can get off of that unstable equilibrium and produce a giant storm. There's no way to return to the unstable equilibrium with the cloud up above you from this event. So specifically what it says is that maybe the parcel, as it was rising, was nudged by a bit of frontal lift. It continued to cool, it continued to condense and release its heat. The temperature of the parcel continued to stay above the temperature of the environment. The parcel continued to be less dense, more buoyant. It continued to rise. Eventually, something upset the unstable equilibrium, and there was no turning back. You know when that point is by comparing the temperature of the parcel to the temperature of the environment, and you can predict what's going to happen as a result. To reiterate, we start with a parcel that is collected right at the surface. We assume that the parcel is dry, that it will follow the dry adiabatic lapse rate until it meets the level of condensation, and after that it will rise with the moist adiabatic lapse rate. So here in this parcel, what you're seeing here is a very different situation from the last sounding that I showed to you in a stable atmosphere. When you look at this parcel, you might notice that it is a lot more laid out in its angle than the steep stand-up straight sounding that I showed to you. And you might also notice that the parcel lapse rate is above the environmental lapse rate. With the stable atmosphere, the parcel lapse rate was stuck underneath the environmental lapse rate. Here it's the exact opposite. The big questions are, will it condense? Yes, it condensed right down here where the dew point comes very, very close to the parcel lapse rate. And what happens next? Does it rise or does it hang? Well, we've seen what the sounding looks like when it hangs out. This is a very different sounding. This is a sounding that is going to show us a rising cloud. Let's understand why. You know about how clouds are lifted off the surface. And you know that this lapse rate in here looks a lot more laid down, like siesta time. And we call it a lay down later lapse rate, if that helps you out. This is a very hot, very still environment at the surface for the parcel. There's no wind mixing up the cool air from the atmosphere with the very hot air at the surface. So what you have is a hot surface, and then the altitude really takes the temperature down very quickly because there's no mixing there. You have a larger lapse rate that is a lay down kind of lapse rate. The larger lapse rate changes temperature very quickly over just a short amount of altitude. As a result of this, the hot parcel that we gathered from the surface will really move in tandem with the environmental lapse rate until the condensation level. And so the condensation level is up here, really moves in tandem with the environmental lapse rate. But after the condensation level, you have a moist adiabatic lapse rate that takes over. And the parcel loses warmth more slowly, so the parcel stays warmer, so this parcel stays more buoyant than the environment, so the parcel can rise and rise and rise. And what you're seeing here is a cumulus cloud buildup that rises all the way up here, quite high, about 14,000, 15,000 meters. So quite a lot of cloud development, cumulus cloud development here in an unstable atmosphere where the parcel was more buoyant. Let's see if there are some mnemonics to help you with that. We say that in an unstable atmosphere, the parcel is unstoppable. The parcel is unstoppable because it is continually warmer than the environment with the latent heat of condensation. And when we talk about equilibrium and unstable atmospheres, we say that if you push on the air parcel and you push it up just a bit, like a forceful lift, it'll continue to go up. It's unstoppable. The atmosphere is unstable. The last thing I wanted you to know about this is that this will continue to rise until it reaches a point where the cloud is not warmer than the atmosphere. At that point, the cloud loses its buoyancy and can no longer lift higher. That point is usually at the stratosphere, where the temperature is warmer than in the lower troposphere. So the cloud will keep lifting until meeting the environmental lapse line at a higher altitude. I'm going to move this over because I think it's important. If you compare morning and afternoon environmental lapse rates, the red environmental lapse rates, think of the morning and a steep gray line environmental lapse rate. Steep is at the start of the day for a slow loss of heat energy from ground to atmosphere. Steep, start of the day. When you think of the afternoon, think of that gray lapse line as being laid down later in the day with lots of heat loss. So I hope those mnemonics help you out too. The environmental lapse rate in the afternoon lays down later in the day. Lots of heat loss. We talk about a larger lapse. This lapse can go about 8 degrees Celsius to 1,000, over 1,000 meters, to about 10 or even 11 degrees Celsius over 1,000 meters. When you create unstable atmospheric conditions, you are warming the ground and cooling the atmosphere, so that in the afternoon you tend to notice those unstable conditions that I talked to you about regarding flight times and airports. Unstable atmospheres in the afternoon mean there's going to be more turbulence in the atmosphere and more chance of a thunderstorm. So fly earlier in the morning. This is a way of creating unstable atmospheric conditions. Heat the ground. Most days the atmosphere is not stable, and most days the atmosphere is not unstable. Most days it is conditionally unstable. That's right in here, conditionally unstable, between the atmospheres that are stand up straight and between the atmospheres that are laid back later. That measurement that we're looking at for conditional instability, which is what the world is at most of the time, is 6.4 degrees Celsius per 1,000 meters. At that average rate, you'll notice a lot of fair weather cumulus clouds. And we have a lot of fair weather cumulus clouds. They're our most frequent cloud across the entire world. So conditional instability is at that level between conditionally unstable at 10 degrees Celsius per 1,000 meters and absolutely stable at 2 degrees or 0 degrees or negative 2 degrees Celsius per 1,000 meters. Just put it another way, conditional instability, and I'm going to take this off of here. Conditional instability can be thought of as the fact that a parcel will need a force lift, convergence, topography, frontal lift, convection. A parcel will need a lift off the ground in general, and then it can warmer than its own surroundings and rise on its own. So in conditional instability, the lift lasts off of the ground. The lift usually lasts through the level of condensation and a little bit above until the cloud starts to lose heat so slowly that it becomes warmer than the environment and it can lift on its own accord without any other force lifting at all. That's conditional instability. Another way to look at conditional instability here, and the fact that most days are in there, is to look at another map of conditional instability. We've got the same absolute unstable atmosphere here. We've got the same stable atmosphere here. There's some more writing in between. You're looking at the middle line here as being conditionally unstable between the moist adiabatic lapse rate at 6 and the dry adiabatic lapse rate at 10, right around 6.4. We got through chapter 5. One more to go. And you're doing really well. See you on the other side.